Thing here. Hi, this is Coffee Compiler Club, October 1st, 2021. And here we still are. We have not yet been killed by COVID. Anything to do with compilers and language runtimes, typing systems, garbage collection, concurrency, whatever, all fair game. Open mic, ask what you want, reserve the right to moderate. You're live, you're gonna go on Twitter, generally within an hour, especially if I can get my secretary, Theodore's not here. He's been taking the timing notes. I'll have to do that. I don't have anything in any set agenda. Talk what you want. That's it. I'm done with my spiel. No one has anything to start with. I'll do 30 seconds of AA update, although it's not very exciting. I've been trying to merge the forward flow and the Hindi Miller typing in my main code base and discovering all the little things that I thought I didn't need or had or didn't have that all touch underlying everything. So it's all playing whack-a-mole, pushing things a little bit left, a little bit right. Twiddle this here and that assert blows there, twiddle that there, and this assert blows here. And after a while, it'll settle out, but it's still pretty higgledy-piggledy.
How much code is there in the code base these days?
Too much. I've been debating like resetting a lot of things. Like I went far down some paths that I intend to go, and then I have to back and redo most of them. And incrementally redoing versus redo from start, sort of questionable which one's better. But this is a question I can answer by going to a directory here, do a word count. Yeah, 176,000 lines. Is that right? No, 160,000 words, 30,000 lines, 31,000 lines. That makes more sense. More than I want for what I'm trying to do, but maybe. Add another soul who's not quite as lost as I am. Are you outside actually, Cameron? Or is that just background? Oh yeah, no sound.
You like my green screen?
Yeah, that's what I'm asking. It's a green screen. Okay, fine. No.
It's actually my office.
Oh, nice. Okay, you lost your roof. Hope it doesn't rain.
I'm outside. Yeah.
Well, if it helps, I'm jarring apple butter. Not the usual jarring, not the usual apple.
Remember, extra cinnamon.
I threw a crap ton in. We'll find out. It tastes pretty good. I threw it on ice cream last night. It was pretty good. All right, somebody else's turn. What did we do last time? It was actually, we had a good meeting last time.
Last time we spent most of the time arguing about operators, custom operators.
Yeah, but everyone can talk about custom operators, so that's always exciting. Yeah, right. I kind of got my head where I want to be with what I'm doing with custom operators at the moment, which I'm happy to summarize, but we did it last week. Yeah, it's fine. And operator overloading, what's the other one? Oh, dispatch logic, dispatch rules, which I've decided on left dispatch and not multi-dispatch.
Multi-dispatch is nice.
I'm sorry, multi?
Yeah.
You have to defend that now because we're looking for a topic change.
Do I have to defend it? Did you
yes,
say?
Because I'm looking for a topic change. No, actually, I have to go do my jarring thing. Back in 5 minutes, so somebody else can talk about Jan. Explain to Jan why it's wrong.
So, yeah, Jan, tell us why you like it.
So I've been looking at Julia quite a lot, and in Julia, the multi-dispatch nicely combines with the compiler optimizations. So basically, you start with a set of functions, and you can, if a function may have multiple implementation, you can multi-dispatch it. But then the compiler can further refine that dispatch by adding cases. That's basically that's the standard operating procedure of the Julia compiler. It sort of keeps adding cases, and it feels like a very nice way, since you have dispatch everywhere, then you can sort of have specialized versions of functions just by, oh, okay, I need, I think I can generate good code if I assume that these two arguments are int. Well, just let me put a version of that in the dispatch table, and voila. So that's
So how often have you actually seen it used outside of binary operators?
I've seen it I mean, so I have data, and the dispatch on multiple argument is everywhere, and more than two, way more than two.
On Julia.
In Julia.
Yeah.
Oh yeah. Oh yeah.
Yeah.
And it makes sense, right? It makes sense that you will. So specifically, if you have arguments that can have multiple implementations, it makes total sense to have versions for each implementation. And there's no reason it should be the first always that you dispatch on.
Yeah, I'll also add that if you have this construct as a first class thing in the language and the optimizing compiler, it's much easier to later optimize, let's say, to virtualize on multiple parameters or specialize for known types of the parameters. Because when optimizing Java, where there is no multiple dispatch, but people still write this kind of code, this is not easily optimizable, because you can have like a devirtualizable multiple dispatch code, but it will be hidden under a bunch of switches on types under several levels of inlining. And now it's a feat for a compiler to actually see through this all to only recognize, well, this is the only target I'm looking into.
You're saying user-written multi-dispatch covering up for a miss in the language is very difficult for the compiler to reverse engineer.
Yep.
Yeah.
Yep.
I buy that. So if you were successful to reverse engineer it, how good is the dispatch compared to a baked-in dispatch that the runtime knew about, like a multi-dispatch? Like, what's the efficient multi-dispatch and sort of the general worst case?
So you mean in Julia or?
Julia, what is Julia's multi-dispatch when the compiler can't discern and it has to actually do a runtime thing?
I think that there's a technical term for that. Shit slow.
Well, that was my point, or my question.
But this is because they, I think partly it's because they never, they didn't really optimize for it.
What would you do then if you decided that this was going to be a hot common thing and you wanted it to go as best as it could?
Well, so, it depends how much type information you can get at any site, but, it's the same kind of thing you would do with single dispatch, right? If you can sort of narrow down the number of types, then.
Right. So the worst case for Java in single dispatch is you do essentially a C++ virtual call. You do a load of the class table and a load through the class table to a code address.
This is wonderful. Yes, it's fast. Who gives
No. It's fucking slow.
No. Wait, let me finish. The reason it is fast is because you're dispatching on one argument. Now, if you actually need the dispatch, so the thing is, if there's benefit in testing two types. So the thing, here's a cool thing about Julia. Julia is an untyped language. There is no typed. Yeah, and no type, but most methods have very precise information because you've dispatched on the types. So you know exactly the types coming in, and you can sort of carry that information while you compile the rest of the method. So yes, single dispatch is fast because you've restricted your coding style to only test one argument. And you have the benefit of that.
I'm asking a different question, which is, how fast, what can you do to make it go as, how bad is the best case fast when you have to do multi? What is your general purpose, reasonable good implementation of a multi-dispatch?
Oh, I don't know about Julia, but it can be just a series of single dispatches. Like, take what you described for Java, a regular virtual call, and then do a multiple of them by the number of arguments you dispatch on.
Okay, so a series of single dispatches, which are, as the technical term, shit slow each one, which is, that's what my expectation. I'm not claiming good or bad, or I'm gonna have to go play jarring games again. I started this because I forgot completely today was Friday. And
Go. We'll be here.
Yeah, and Arthur, if you're willing to burn some space, I mean, it's an M by N problem, right? Except
Yeah.
it's M by N by O by P by Q by R or whatever. But if you're willing to burn some space, you can reduce, to the known set of types in the axes, and then multiply, add like an array axis, and get a single function point. So in theory, you can trade off space for time and approach single dispatch speed with a multi-dispatch.
But
The
Yeah,
problem
and-
is that subclassing makes everything more complicated, because it's like if you have trees of types and you're dispatching on those types across multiple, MNOP variables, you can't fully, you have to first reduce those types, otherwise the table is going to be, petabytes large.
so I think generally speaking, the question is, how often do you have many types for each of your arguments? Once you factor in all the static type information you get at the call site. And yes, the worst case is it's going to be a bunch of dispatches, and that's kind of slow. But how often does that worst case occur?
Yeah, we know about single dispatch that in most cases, at least for Java, in most cases, it is a monomorphic call. And I don't have data, but I can assume that, yeah, in many cases, multiple dispatch might also end up with a single target in runtime. And in this case, if there is the virtualization for this kind of dispatch, then the conversation about the cost of doing the actual dispatch is not that relevant unless you're actually doing a megamorphic call.
Yeah, the huge count of Java calls don't go the slow route. Most of them go the fast route.
And that's a good question. Like if there is a language with multiple dispatch, whether this property holds true for multiple dispatch or not.
Jan, you said you had some numbers on this. I know you like to grovel through GitHub repos.
Yeah, so I need to dig them out, but we had numbers in 2018. We sort of did some look at Julia, and we had numbers on how many overloadings there are and how many of sort of a bunch of these things in that some OOPSLA paper. So these are findable.
You have any?
Julia has another reason why dispatch has the speed I described, is because their subtype algorithm is incredibly complex, and so it's not the simple nominal typing we know. I mean, actually, we know that it's not decidable. So their subtyping, we can sort of kill the Julia compiler in 3 lines of code. Yeah, that's a sort of orthogonal to the is multiple dispatch a good idea?
Yeah, I've only worked with one large code base with Julia where they went crazy with multi-dispatch. And it was actually, from my point of view, it was very difficult to tell what the hell types were and who was going to get called by what, because the rules were somewhat complicated and the implementation, I mean, people there went crazy with their typing schemes. So I had trouble finding out who was going to get called.
Yeah. And that may be a big downside. But sort of going forward, sort of talking about things that would be cool, I think it'd be nice to sort of make the dispatch even richer. Sort of, why just type of arguments? Why not other predicates of arguments? Such. So now with languages like Rust, you want to know that something is unique. Well, if I have a method that's taking something that is unique, I can maybe do something more efficient by like updating place versus copy.
But you change the language semantics, because if it's
sure.
unique, there's like ways the compiler can tell a lot of things are unique. If in Java you make no class, you never call new on a class, you got no instances. If you call new exactly once, you got the one golden instance,
Mhm.
and the runtime
Well,
knows that.
So
there's-
unique, I meant a unique pointer that, this particular instance has currently only one ref to it.
Oh, I'm sorry. Okay, so it's like
That-
linear
that-
logic or Rust style
Yeah.
something. You know that you're the sole owner.
Right.
That's an ownership type.
Yeah, yeah. Or I work with R and you have a ref count on objects, right? So if I'm getting an object that has a single ref, I can, update it in place, good for me.
But I'm asking then, or what I heard you say was the dispatch rules would change if the ref count was 1 or greater than 1.
Yeah, you could dispatch on that. That's a property. I mean, why just dispatch on types?
Okay,
Types are
and now is
boring.
that
They're
better or
static.
worse than saying if ref count greater than 1? Right, this is the Arthur's proposition that, yeah, I can do it, it's just really hard, or it's only in limited cases. So like, if it's commonly the case, I'm going to do something special for ref count 1 versus ref count 2 or more, then there's room for or mental syntactic sugar, weirdness in the language you can learn and take advantage of this. If it's a rare event that I'm going to do something where ref count 1 versus greater than 1, that I claim you shouldn't throw it in the language, you should just make it part of the normal.
So
Right,
here's
yes.
my argument for why it could be cool to have in the language. So my point with the multi-dispatch and the Julia compiler was that the Julia compiler sort of so since multi-dispatch is burned in the language, the Julia compiler leveraged that to add overridings to the methods with specializations. So if you could have some kind of contextual dispatch burned in the language, then it would be natural that, and since my compiler knows things about the calling context, it
Right.
can generate also specialization, and that becomes completely part of normal execution.
Well, and what I'm asking then is, how often would it come around that I would do this? Like the times where I take advantage of the uniqueness of something to update in place versus copy on write, for instance, means I'm doing a system-y style low-level thing where I'm thinking hard about object lifetimes, and it's easy to screw this up and get it wrong and break yourself. And I've done this with manual no compiler support any number of times, and I've watched other people do it or not do it, and it's kind of you eat it all at once or you don't. So Lay's potato chips.
So here's an example case. So say that I write this function that updates a 10 megabyte array.
Right.
And I would say I should only run this function if I know that I have a single ref, because otherwise I'm taking a huge copy hit.
Right.
Right. So you could say, well, I put that in the dispatch mechanism, and if I don't have that, then go to the default.
Well, I would claim
do this.
I would claim that particular case I would solve by saying assert ref count equal 1 and not have any dispatch change.
Sure, but that's one example.
I know.
I work with a language that has laziness.
Okay.
And I would like to know that this is not a closure. There's there's lots of properties that you could think of dispatching on, and definitely your compiler will benefit from having that. Benefits. I mean, so in our JIT compiler for R, we do all of these things. We have a sort of this context dispatch, and we dispatch, but that's behind the scene, hidden from the user.
Right.
Just like
Right. I'm saying language implementation, systemsy things always want something different than like the guys who are writing J2EE apps. And I don't know, what's your target audience?
I don't know either. I mean, it's the same audience as AA.
Yeah, exactly. Oh, I'm totally staring at it. There are things I want that I'm pretty certain not too many other folks will care all that much for. And I'll have to, pick and choose here.
But in some sense, the more we can put in the dispatch, so the way I think of it is, in Julia, you're sort of front loading all of the type test to the interface of the function. That's what multiple dispatch does. The alternative is you have a single dispatch, and then you have a lot of if cases, and you have all these little.
Arthur's been fighting through. Yeah, right. Yeah.
So in some sense, the more you get the programmer's help to tell you which are the tests they can do early on, then the rest of the code you're compiling is cleaner, right? It knows that these are all facts that you can assume. And that, I think, it's good for the compiler, but it's also nicer in terms of code to code. Well, you don't
It does introduce the M by N problem though, right? So I mean, if you're talking about a matrix of 2 by 2, I think it's a perfectly reasonable approach. I think Julia does fine with binary operators with multiple dispatch. I mean, it works. Not my cup of tea. I mean, but I think it works in the language. But the problem is what happens when you have 200 by 200, and that's for 2 parameters. What if it's 3 parameters and it's like the numbers go up really fast. So I mean, I like the way you're thinking.
When you mean 200 by
perspective.
200 is 200 different cases?
Yeah,
There's some bushy, functionality going on.
Well, there's
Exactly.
2 choices. You can run it slow, and that's fine.
I'm not worried about the slow versus fast though. I'm worried about
The semantic
you're
overload.
transferring the complexity explosion onto the interface itself, right?
Yeah,
So
yeah.
I mean, I like to do that when I'm generating code, right? But I don't want to do that in the source tree. So, kind of what you were saying about the dispatch made sense, which is you want the system to be able to discriminate early. You want it to be able to discriminate at call site or back it up a call site, right? And so you want to be able to choose a discrimination point and then inline on down, knowing all the types. So, using, Arthur's, monomorphic optimization, Arthur's clips, whatever, like you say, okay, are these assumptions holding? And if so, I'm going to inline all that. Otherwise, I'll go the slow route. But if you transfer that bushiness, as Cliff said, to the developer, then they have to make sure they fill out n dimensions of the array completely, or something messes up.
There's another aspect here, and that's the rules on which you go the slow route versus the fast route become complicated, hard to understand. And the slow route can totally be in your hot innermost loops. And that's exactly what Flavio's always complaining about with the endless interface style dispatch logic. Basically, every call goes down I'm doing an interface call the hard way. They're all doing effectively multi-dispatch with a bad linear search. And it's slow. And it means your entire programming model, your entire language is slow because there's no fast or efficient way to go do dispatch. And I don't have a good answer in that sense, and I don't know that Julia does either. It's just like you bought yourself into a world of hurt where you're doing in code what maybe you ought to be doing with reified types and big ass array. 200 by 200 array is not a problem. 200 dispatch is.
Have to run, guys. I'll see you next week. Sorry, I have another call, but
yeah, nice seeing you.
Yeah, bye.
Okay, yeah. Well, we lost our Julia fan. He and I worked on the same project for a while. Big ass giant Julia project. Has a lot of.
He has much fonder memories of that project than you do.
Yeah, well, I need to go call those guys back up. We came to an agreement that if they restructure, they rode into town on the wrong horse. If they restructure their underlying data structures and change the horse they're riding on, I could give them a 10-fold speed up on a performance critical entire language implementation. It's a database with a different, a different way to do, not SQL. And they have to do, TCP/H queries, and they have to do performance, and they have to be at least close to competitive, and then they'll make up with having a nicer language to write than SQL. As a business model, you have to beat SQL. It's not that hard, but you have to be not so performance stinky. And I looked at them and like, okay, guys, you're leaving 10x on the table. They're like, no, we're not. So I gave them a demo. I ran SQL queries. I ran TCP/H queries on H2O, and I can tie to slightly beat the best of the best of the best scores out there. But of course, I'm not a database, so I get to cheat in a few ways. But it's pretty clear I get fucking close. But that required a complete data structure thinking change, and Julia was not the horse to go ride that particular job on. So I don't know. We went back and forth. I helped them with their Julia problems for quite a while. I got them a 2 or 3x speed up without too much trouble. But to get more than that, they're going to do a complete data structure change and get away from their beloved multi-dispatch, which was gone hog wild and made it impossible to figure out what's going on and made it impossible to optimize too. Fine.
So we ran into a weird one this week.
Excellent.
Mark wanted to bring it up.
The baton just got handed off, Mark.
Oh yeah, we can do that. So I can see if I can summarize ecstasy concurrency properly, and then Cam can correct me where I'm wrong. Right. So it's the only parallelism in ecstasy is the services. Right. So two services can run completely in parallel on two different cores, but within a given service, you have zero parallelism, but you do still have fibers. And so fibers can basically do cooperative multitasking and switch off, but you never have two fibers actively running at the same time, but they can still switch off. And the switching point is controlled by code, right? So there's no, it's cooperative, right?
Okay.
So where does it switch? It switches when a fiber calls out to another service and blocks to wait for the result. At that point, like a new fiber on the originating service is allowed to take off, or another one that was suspended is allowed to resume.
Right.
And you can set concurrency modes on the service to limit that, right? So you can set it to forbidden, and then you only ever have one fiber. Then what's the next mode? Exclusive, is that right, Cam? I don't know. I find the modes confusing, but there's
open, prioritized, exclusive, and forbidden.
Yeah. So as you move up towards open, once you get to open, like anything can happen, but it can still only happen at these predefined handoff points.
So you don't necessarily need a CAS operation within a service, but maybe just when you do handoffs.
It's anytime the fiber would block.
Yeah.
But of course, the only reason you could block is because you called out to something external, which is then represented as another service. So if you block, like another fiber comes in.
Got it.
And then the extent of concurrency control outside of setting these policies is you can define a critical section for code, which I always look at is very similar to Java synchronized, but it's at the service level itself. So while your code's in a critical section, even if you block on another service, another fiber can't come in on your service and swap you out. And that's the extent of concurrency control. And I think from the stuff Cam's talked about before, there's no mutables crossing between services.
Okay.
Everything.
Can you deadlock? If service A says I am holding I'm exclusive in this guy, and I called out to B, who calls back to A.
As soon as with exclusive, you'd be okay, because exclusive literally means you can yield kind of to help yourself. But forbidden, you could definitely deadlock. Forbidden, if you call out to someone and they call back to you, you're deadlocked.
Okay.
So in a deadlock for forbidden will end up in an exception. Yeah.
Yeah. So you detect the deadlock, which is fine. And then the other question was, is there an easy knob to say I want to replicate the service in number of times?
Yeah, the service is just a class. So instead of saying class C, you say service C, and then you new 50 of them. So.
Okay. So there's an easy way to scale up.
But we haven't yet talked about the problem that came up, which was interesting. So, and to pat myself on the back, I think I've been uneasy with some aspect of the concurrency model for a long time, and I never described it very well. But I always kind of said is the fact that whenever some piece of code waits for another service, you can have switch fibers. That effectively becomes like plain old concurrency programming. Like if I write some code that calls some code that calls some code that blocks on a service, all of a sudden, 8 layers down on my stack, like to me, the world changed and I don't know why.
Right.
And so Cam hit one of these this week where
I spent 3 days debugging.
Right, which is, again, it feels just like a regular concurrency bug, right? So a normal skipless data structure called out to a service, and that was enough to trigger a yield.
Yep.
And like it came back, and somebody else had another fiber had re-entered and modified the data structure, and like
Yeah,
everything,
so let me-
the world changed.
me
Where
every
start-
blocking point is a complete, all your data structures got shuffled. Yes.
So let me start by saying the problem was caused because a service was injected into a skip list map. So a skip list map does what's called a coin flip for
I do
determining.
not like injections. Fine.
So skip list data structure,
Yeah.
basically it's a bunch of linked lists, right? So you have a
I know what you
every linked list, every other linked list, every fourth linked list, every eighth linked list,
Yeah,
and so on.
I know what a skip was.
So it's kind of like a balanced binary tree, but turned on its side, right? So it's a 45-degree off tree. And it's a really cool data structure. I love it. I loved implementing it. But and because it's so expensive to make it every other one and every fourth one and every eighth one, you instead flip a coin to figure out if it's supposed to be every other
Yeah.
one. And
Right.
then you flip another coin if that one was true, and that gives
Right.
you the every fourth, and
Right, no,
another
that-
coin.
yeah.
So basically, you ask for random int, and it tells you which buckets to fill in, right? Based on the, not on the pop count, but on the trailing ones or trailing zeros or whatever. Basically how many bits in order. So in a row, and so you're deep inside, right? So you've already figured out I have to insert something, right? So you're finding an insertion point, right? And you're flipping a coin on how many pointers to put in that node, basically, because each node has a variable number of pointers based on the coin flip.
Oh, I have a
And,
bug for you, but keep going.
And so you've already loaded some structures into your registers. Here you go, you load your array, you load your size, you load this, you calculate something. So you've got all this stuff set up here, just perfect, right? Ready to do your insert. And then you got to flip the coin and God puts you to sleep for 30 milliseconds, right? Because it turns out that your coin flipper got injected in and it's a service. And by calling that service, you suddenly, released your service to be able to start a new fiber because you've gone off to a different service to calculate a random.
And it's interesting here because where I think you were amazingly lucky is the data structure that got corrupted was also the one that called out to the other service. And it could have been that those lines of code were separated by many classes. It wouldn't have been 3 days of debugging, right? It would have been 4.
So I'll have to say that I've done many concurrent algorithms, and the theme that for me that works, this is true concurrency, not service split with yield points, but it's the same issue, is that you have to read a bunch of things, do your state tests, decide that you like the new world, that you know what the new world's going to be, and CAS once without ever reading again. And if you
But
can't
we're on a
arrange yourself
completely
that way, you can get
We're on a
busted.
completely different path though, because the whole purpose of this design was to say, CPUs are designed, CPUs and memory subsystems and caches and everything else, they're designed for single threaded throughput, right? If you want to do concurrent throughput, you trade off a pretty dramatic amount of throughput per core. So the idea is
No,
yeah.
no, I
Because-
routinely get my cores maxed out, but it takes some thinking about the problem a different way. But
You have the CASs, but you're avoiding the contention on them, right?
yeah, yes, and the fact that it's a CAS and not a lock means that I can actually eat a fair amount of contention on a CAS.
I don't know.
But your
The
contended
CAS
is also
You can beat yourself to death on a CAS. No
L3.
question. Sorry, Cameron.
Yeah,
Say again?
no, I'm saying your CAS is wiping out someone else's L3.
If I've set myself up right, I can guarantee you that some CAS makes progress if everyone has to fight on a CAS. But the real trick, of course, is that the CASs are there for your safety and you badly don't want people beating on the same CAS.
And by the way, if I ever need someone to build me something in C to, keep 128 cores
Well,
completely busy,
Java, I did it in Java too. It's all good.
right. But the point is, how many people do you know who can do that?
See, here's the trick. I have a stylistic way I write this shitty code, and I don't see other people talking about it. So I'm like, well, maybe your problem is that you need to be writing your code this way if you're going to be writing concurrent code. And maybe, the answer is there's no way to write code that way, or it's not a general.
But yeah, I think the point is there's not nearly enough people that can write it that way. And with Ecstasy, kind of the way I always look at it is the promise is you just write single-threaded code. Like the vast majority of people do not need to write code thinking about concurrency. And if that can be made to work and perform, wouldn't that be nice?
You just fell into a concurrent bug, so I claim you're not there yet.
Well, yes, exactly.
That's why we're raising the topic.
This is my claim for H2O as well. You wrote single-threaded math algorithms, and I auto-parallel, auto-distributed for you, and it mostly worked. But you had to have some sort of, it was a limited domain. You had to have math on big arrays. That was all fine.
Yeah, so where we find ourselves now, at least the way I'm looking at it is, it seems too easy to get into this position, even when you wrote the language and the data structure and probably the service that it called out to,
Yep.
right? So it's what could potentially be changed to, make it safe and still be performant.
I went away from call out to blocking and return to continuation passing style in H2O eventually. I mostly started with call out, block, and return. To fix deadlocks, I had to go to cluster-wide lock ranking because they're constantly adding and subtracting locks, big ass asserts at compile and setup time. There was an engineering thing that let me continuously evolve an H2O instance with new code that you had to get through to prevent the deadlock problem. But and actually that was the same as your performance problem too. That you get your parallels in back. But that still left you subject to what you just said, which was I called out, I blocked mysteriously because I went umpteen layers deep. When I came back, the world changed. And that was me. My fix for that was switch to continuation passing style. And the set of things you did was in a chunk of the continuation, you would test some set of things by reading everything that you needed to test exactly and only once. You cannot test if you don't read it. And if you test it twice, if you loaded it twice, you got a different answer both times. So your first answer was crap and you had to start over. So you got to load everything once. You tested everything. You did a CAS if the world was good and the CAS won, and then that was the end of your continuation. It was a funny style. And once you got your head wrapped around it, I never had concurrency issues again, except that you had to wrap your head around writing this way. So, what do you want to do about that? I don't have it formalized.
We sliced it a much different way because because your typical developer is not dealing with shared mutable data, firsthand. Right?
Oh,
they may be dealing with it.
You got it because you said I crossed an arbitrary code boundary, which was a call, which I didn't know blocked, because the injection happened behind your back. You didn't realize it blocked. You made a call. You crossed a call boundary, the world changed before and after. That's the same as concurrent coding the old school way. That's the model you need to not let happen to you if you want to have
specific, people and specifically, this is in a very high contention junction box, basically. So where this happened is the transaction manager. So the transaction manager actually gets pummeled by every client. So you have 100 clients pummeling it, and you have, say, 100 different data structures that make up the database. So they also are talking to the transaction manager. So it's a natural point of contention, right?
Yeah, H2O, Java hotspot, full of these. Yes, fine. You have to deal. What do you do? And that's what I'm saying. When you come to that point, there is a coding style that works. So carry on. Sorry, I'm interrupting. I'm all excited.
Well, no,
the question is, can you enforce the style? Can you enforce the style by programming language design?
Yes, exactly. I got kind of close enforcing it with some amount of rules and some amount of boilerplate at H2O. Clearly, it needed more language support. I didn't have a good answer how to do that. It's been in my head when I'm staring at AA all along here. So I don't know if I'm going to get there or not, but I definitely want to think hard about how
So
you let that happen.
The idea behind having the service model in the first place is to make it extremely cheap for a developer to spin up a mutable space that would run at most one fiber at a time. And if they wanted to spin up 200, more power to them, right?
Okay.
So that fiber represents that continuation.
Right, you're close. I think you're really close. Your issue you had was you exited your service and came back into the same service. Whereas if you exited and didn't come back into the same service, that's continuation passing and you've been okay. But because you came back in, the world changed and you didn't realize, and you reused the old world knowledge, which was invalid, and you had to reload the world again.
Right, it wasn't supposed to 7 levels down or whatever Mark said, 9 levels down. It wasn't supposed to say, okay, I'm giving up the schedule.
So the fail here could be you allowed an injection of a service inside of another service that broke the invariance in the first service. The injected service lost his standard invariant of nothing changes out from under me when I cross a call boundary. And
that seems to move in the direction of saying, like, it would naturally lead to you never use services, but in ecstasy, everything is services.
Well, not you never use services, but that you agree that when I cross this call boundary, one of two things happen. I am guaranteed before and after are identical, and now you throw your exclusive flag on the service, or I guarantee you that your world got trashed and I must restart from scratch, but that's basically a new service boundary anyhow. And that's your continuation style. You cannot call out to another service and expect to come back. You can only continue to a new thing, which, because it's new, it had to reload the world anyhow. And
what's super funny about this is we expected this to happen with IO services, and we expected this to happen with, so like we were we had all these things that we would have expected to occasionally, hit us in the shins, but it was a freaking random service that bit us.
Sorry, I've been down this path so many times. Every possible place eventually gets hit. Eventually. And it doesn't hardly matter. The frequencies are low. Unless there's 0, it's going around a billion times a second times a low number. It comes around.
It is funny, though, that the first one was here.
Oh, and by the way, I threw in a quiz for people here in number 3 in the doc. What is the expected outcome for your random number there? Single threaded, for I equals 1 to 1,000, pick your random numbers. Add the first 1,000 bools up. Anyone want to venture a guess?
500. It's got to be.
Excellent guess. Anyone else?
But Cliff, you told us this one before.
I know. Well, so you don't get to say because you know the answer. All right, I'll tell you the answer. The answer is 0. The first several thousand, 100,000 randoms out of Java suck until the seed gets scrambled enough to start doing something good. So the bools grab the low order bit, which is always 0 for a very long time. Yes, what? I see Cole going, what? They fixed that in later versions. You should start grabbing some Java versions, write this tiny piece of code and go do this. This was H2O doing random numbers exactly for skip list, not skip list per se, but doing a distribution and discovering suddenly that the distribution sucked. And that's why we were having performance problems. And where did they suck? And we kept going round and round and finally drilled it down to the random number generator sucked. So one of the big hacks we did at H2O was we come up with a really nice random number generator that was completely pseudo-random, could be run distributedly and pseudo-random. So you got consistent, identical pseudo-random numbers across the cluster, independent of all other things. You could start it in the middle and stop at the middle. You could hand out 1,000 to 1,000 nodes and it all march their own independent paths. But pseudo-random good enough that you get your right kind of distribution and the right kind of skip list properties. You're using randomness to get, avoid a hotspot. Exactly, to avoid a hotspot. So the randomness prevents you from accidentally piling in on the same thing. And of course, if it's all 0, then you all piled in on node 0 and he sucked. Fine.
Wow.
Fine, how'd he do? Yeah, well, I encourage you to think carefully about your how you're going to handle how are you going to handle side effects when services can call out and somebody else can run behind you? Because I think that's the goodness and light of your model.
So that's what we were pontificating about, thinking about this week.
Right.
And there's that whole async versus not async coloring model. I don't know if you've read about that. I think York mentioned it.
I've been down that path. I've used that in JavaScript land. It sucks.
Where you basically end up with two of each method. One is async and one is not. But that kind of concept where so you can always go from red to blue, but not blue to red. Does this ring a bell? Anyone from previous conversations we've had?
Not here. I mean, I'm familiar with what you're talking about because I've lived it.
Yeah, I mean, we've discussed it a few times, but it's been a while back.
It's a painful way to have to write everything twice.
Well,
Right.
yeah.
And that's what we were trying to avoid, obviously.
Right. Well,
but Mark's comment was, if you could color the methods and say, I'm safe or not, then the idea was that unless your entire fiber creation point to current point call stack is safe, then it's unsafe and you don't yield on you don't yield on an asynchronous call.
Safe meaning I'm willing to have the world change out from under me.
Yeah.
Right.
See,
Which is interesting because it's the opposite of what's normal, right? It's kind of like synchronized by default, right? And you have to opt into concurrency rather than today we have to opt out of concurrency, right? Which is kind of suggests that all code is thread safe by default, which of course is not, right? So this says go the other way, right? Assume all code is not thread safe, and only if you are, I mean, I'm saying thread safe, but it's the XC concurrency model.
Right.
Only if you are safe for reentrancy, then you declare it. Now you're eligible for having the world flip on you.
Certainly the H2O model was you were not doing anything concurrently that you were aware of unless you started asking for it by saying shit like non-blocking hash map. Then you were volunteering your way into it. Otherwise you were single threaded, apparently writing code. And of course it was parallel under the hood, but the rules were there. When it came to the system guts of H2O, as opposed to the math you wrote, you had to follow the rules manually. But the general rules, like I was talking about, you ended in a continuation and then you started up again after the blocking site, knowing the world had been fucked. So you didn't do calls so often because they were weird. Instead, you did continuations. You forked, and the forked process picked up, your execution, but he had to reload everything, and that saved you from the concurrency bug. But it was a pain in the neck to write the code. So I'm hearing your service model. I like it conceptually. I think you have to agree that you can't call out, or you have to volunteer in. Yeah, maybe you could volunteer in. I know that I'm concurrent safe, which comes with giant red flags saying,
Well, we have basically three categories of classes, three categories of objects. We have immutable objects, we have service objects, and we have other. And the other is basically mutable things that are not, so what Java calls a class. So everything in Java is mutable.
Yeah, right.
Class, right?
So you have an immutable, that's nice. And you
so
have
immutable is easy, right? So from a point of view of reentrancy, it's like, fuck, I'm sorry. Just reenter as often as you want, right?
Right.
And then service is like reentry, like I'm a service. I don't, I know everyone's calling me from across some, gulf. So the only one that poses the problem is the mutable data structure, the class, if you will.
When you got hit by a shared concurrent hash table implementation, had to be a skip list.
Right, but that's the
you need those.
But shared is the wrong way to look at it. It's not that it's shared, it's that it's state of a service. So the service is maintaining some of its transactional state in a skip list, right?
Yeah.
And so you have a fiber that's making a change to that data structure, and in the middle of the change, it's frozen because it.
But that's the thing, it is shared, right? It was just shared with other fibers, which
right. It was inadvertently it was inadvertently shared in the middle of a mutating operation.
Yeah. And you know, I claim that you got surprised because the injection was surprising. That Rand made a service call.
Yes.
Wasn't obvious.
Yeah.
And then
it's completely hidden behind an interface. Exactly.
right. And that's what I'm saying in how I was coding this elsewhere, that calls were suspicious, you didn't know. So you had to have some kind of rule attached to every freaking call. I bottomed out in a blocking call or I did not. And if I bottomed out in a blocking call, I had to know, you know, the world got trashed when I came back. And, you know, I tried a couple of things like signatures that were funny. This call blocks, so it throws in the check exception. And I had to agree to throw the check exception that no one cared. And it actually was no exception, never throw it, but it was just a typing.
So it's kind of the coloring thing we were talking about.
Yeah, the coloring thing. This blocker didn't. Yeah. And usually the story then was if I was calling one of these blocking calls, there was no sensible recovery after it other than a continuation. And then it was just better, just easier, just do a freaking continuation. So it, you know, it needed a language support. Fine. If you ever coded in Elm, Elm's
I've looked at it. Yeah.
First, it gives a code in it because your head gets twisted in a funny shape, but it's the same shape that H2O got twisted in. Everything is a continuation because it's calling into the browser, and then the browser does stuff and calls back with events that come from all over the map. They're always single threaded in the code you write. It's always immutable and state free, and then you return a state to the runtime, who then randomly shuffles and you get called back in a different call site in a different place. But when you write single threaded code with blocks in the middle, what it really turns into is continuations every time.
Yeah, and that makes sense until you try to express the code where you can block in the middle of your method, right? So like when you're forced to pop your stack before the world can change, all of a sudden you're always programming defensively.
So in the case of Elm, they made it so that you couldn't block, but you wanted to. So instead, if you made a blocking call, you got told this is a continuation. You have to tell me the continuation that comes after this blocking call. And you got language support to set up, here's the rest of the computation after the blocking call returns. So you got the language support for it, but you were forced to wrap your head in, I'm doing a continuation right here, right now. And I have no option. There is no option other than I must do continuation, which kind of sucked and kind of, like I said, twisted your head, but suddenly you had compiler support for it.
So was the idea there that because it forced you into writing a continuation, it forced you to think concurrently?
Kind of. It forced you not concurrently. It forced you to break your computation up. There was before the block, there was after the block. And
it became very apparent that the world may change before you get to the after the block.
You had to decide what you were going to hand off from before to after. So you couldn't hand off any state from before to after, because there was no state you were going to cross that line. That was the point of the continuation. So you gathered up what you needed for the continuation and you put it in an immutable data structure and you handed it off to the continuation blocking guy. And when you came back in, that state was what you got to carry on your continuation. So the suck part of this was you had to list all the things that you were going to use in your continuation. And the great part of this is that you listed all the things. And because you listed all the things, everything else was not listed, was not part of it, and you never got it, and you didn't need it, and you didn't have any mystery, no background things moved out from under you because you listed all the things. So it forced you into a continuation style. Kind of ugly. Some things, like I said, some things worked out really well, and some things kind of felt like sicker than hell. Like random turned out to be a blocking call, so they could go to the runtime and get random bits, which means every time you made a call across a random, like I've got a random to do a game design thing. Well, randoms show up everywhere. This guy shoots now or he doesn't. The die roll for the damage, the direction the AI moves, whatever. Every one of those had to be a block continuation go. It sucked. For random, I'm doing big old screen paint of a million element fintech data set with pan, scroll, zoom, and real-time feeds coming in and all kind of analytics running all at the same time. Worked great. It was fantastic. It was fast. It was easy. It's obvious. Mixed bag. Some was good, some was bad.
So Mark and Cameron, if I could ask, your model with services is like tantalizingly close to kind of like Erlang. And I wonder if you guys know anything about Erlang, and if you could kind of comment on where it diverges. Certainly you guys seem to emphasize the ability to have some mutable state, whereas Erlang, their little services don't really have mutable state, but they are little like isolates. They only communicate over channels with other little isolates.
So I've
I
never
mean, it's
coded
like
in
very
Erlang.
similar.
I've never coded in Erlang or Elixir.
Sure.
I've looked at it a bit, and a lot of people have compared what we've done to Erlang. So I consider it a compliment. I'll take that. Thank you, Joe. Joe Armstrong.
I'll say, Cameron, I'm very interested to see how this works out for you, because what you're doing sounds like a step in the right direction, definitely, and you know, you've got some good stuff going on.
So what Erlang did, they had an object called they didn't have objects, they had what they called processes.
That was their equivalent of threads, right?
Yeah.
So, well, anyone who knows Erlang, correct me as I go, but every object was a process, and every process was basically a queue and a thread. Not in reality, because it would often be running on a single hardware thread on a
there's a lot of optimizations you do in these models, but that's independent of the semantics.
So basically, every call to one of these things would either transfer control to it or stick it in the queue. Right? So every call was a message. So it's not like they had classes of objects and then asynchronous classes of objects. They had just asynchronous classes of objects. So everything was asynchronous. So that's kind of the big difference between what we've done and what I understand Erlang to be, is that, you know, basically in our model, a developer explicitly says, I want this to be an asynchronous junction point. I want this to represent some field of mutability. That's what we call a service. So our service is very analogous to a process in Erlang. It's just that we also have things that are not processes.
So
is it in Erlang there's no mutable state anywhere?
There's no mutable state.
It's a global database.
But there's the global database, yes. So that's a big mutable, like, and they have, of course, had to code that really carefully, like in C or whatever.
The file system is pretty mutable.
And the file system, and
but you don't have to code that one. Like, kernel guys do that one.
Right.
Your file system's a giant, big, shared common database.
Yeah, but you still have to deal with the concurrency issues. Like, you don't have to deal with the explicit locking, but you know.
Yeah, but same as any other large shared common database. If I non-blocking hash map, large shared common database used for.
So who has used Erlang or Elixir out of this group?
I have.
Nice.
So tell us more. Was I close to correct what I was explaining?
I unfortunately missed part of your explanation.
Well, I was saying that so Erlang. Well, first of all, Erlang is very non-strong when it comes to type, non-strict. It's not a statically typed system. How's that? Everything is typeless, I guess, kind of.
Everything is tagged. Your messages are tagged, generally.
Tagged, and then but each object, if you will, is what Erlang calls a process, right, Max?
Each object? No.
Well,
are there any
doesn't have objects per. Erlang doesn't have objects.
You have structures, and you have maps, your usual types. The actual asynchronous part, that's just processes. And processes, you don't really use them like objects. You get a PID, which I guess you could call it an object, but you have regular structures basically
within a process.
Yeah.
No, like structure is just a type that you can create, like an integer.
Can you pass a structure across in a message?
Yeah.
I believe so. Basically, everything on a local node, and then if you do it across network, I think there's some limitations where you can't send functions across the wire, but I'm not entirely sure.
Okay, but you can send arbitrary structures, but everyone gets their own private read-only or whatever. They get it.
They do deep copy. Although if the object is, I think it's larger than 64. I'm not sure if it's 64 bytes or kilobytes. Then it uses reference counting.
Yeah. Okay. And copy on write then. If you semantics are, you have a
You generally
private
can't
copy.
write.
I'm sorry?
You generally can't write. Like if you have a structure, the way you modify it is you do this whatever it's called, like a spread, and then you do like a lensing type thing.
It's a copy on write, basically.
Okay.
But it's explicit. It's not implicit.
Okay.
Yeah.
But I make a new structure by a delta from an old structure.
Right.
Yeah. Okay. Which is what Elm does and a couple other languages do.
Yeah. Haskell, everything. Yeah.
Yeah. Okay. Fine. Yeah. So all data structures are immutable, and you copy the hell out of it, and you hope the runtime optimizes with ref counting under the hood and private ownership rules, and so he can optimize some amount of them. But everyone's okay. Fine.
Well, the thing is, you're not doing like big number crunching. You're just doing like, high level coordination activities. You're not like, oh, let's.
It's the other way around.
Yeah.
The reason you're not doing big number crunching because it sucks to do big number crunching.
Right.
Well, you wouldn't want to.
Number crunching because no one ever needed to do big number crunching who used Erlang in the last 30 years.
Okay.
So
but if Erlang was good at big number crunching, you can bet people would already be whacking away on it with big numbers. I mean, big crunching, but they don't because it sucks at it. And so there you go.
Yeah. That's not what it was meant to do. It's communication software.
Yeah, but any highly concurrent async. So I claim the browser interface to your mouse and keyboard is a similar kind of crazy. They're getting reports back from 13 websites, and all their databases are coming and going, and you're getting mouse clicks, and you're getting repaint events, and 200 async events are going off continuously, and how do you sort it out? And that's reactive coding, and that's the whole continuation versus async await or whatever, all of the above.
But the model that for the programming model for Erlang is much more pleasant than in the browser, because you set up your process and you say, I'm going to receive messages, and you just write a function that it's like a switch case on the message.
Yeah.
And that's it.
Have you ever coded in Elm?
No.
Okay, it is very similar. It's Haskell typing scheme with true, it's for the browser. It's heavily integrated into the browser, and it's you write single-threaded code with the switch statements that do the breakout of things, all kind of helped along with you by the language semantics under the hood. And Elm being the name of a tree, you have to go for elmlang.doc. I think that's the right one. If you guys are all looking, actually, I'll throw that in the elmlang.org, one of the two. Here we go. Did you mean yes? Okay, this is a good. Here we go. I'll put this into the docs because I'm stupid. Yeah. Well, let me put the answer for the thing here. Sorry, updating the doc. Random thing. So this is see how hot is this? Pretty hot still. This is my this is the reason I was late this morning. This is my apple butter. Nice. The lid has properly sealed.
Hey, that looks like about 600 apples.
No. It was one Homer bucket made a dozen jars, half a dozen jars, plus I got some spare.
So one for each of us?
I have a lot of takers for this. My old apple trees, the old house, by the time I left, I'd be having gallons and gallons and gallons to give away. The new ones are still little spindly, scrawny things. So I'm going to have 6 jars here. I might get another 6 later in the season. And I'll probably make some pies and some other stuff. It's not going to be a lot of spares. And, my family.
I'll take a handle of Calvados.
You'll take a handle. I'm sorry, what?
I'll take a handle of Calvados. Calvados.
Is that the distilled cider?
Yes, French.
I don't do ciders.
I do ciders. I homebrew cider.
There you go. Yeah, I like ciders.
I see a strong friendship in our future, Max.
Are you in the Bay Area?
Hard ciders. I can't.
Bay Area apple meetup.
There you go. Bay Area. Are you
Unfortunately,
Bay
no.
Area, Max?
Yeah, I'm in Burlingame.
Oh, nice. Okay, yeah, I'm in Sunnyvale. I'm, quarter mile from the Sunnyvale train station.
I used to
Yeah,
be 50% Bay Area, and that was 50% too much most of the time.
Come around and bring cider, and I'll send you home with an apple pie. Yeah. Oh, freshly baked on the spot, no less.
This is compelling. After I get back, I'm going on a trip to Boston, but after
Yeah. Well, when's your cider ready?
It's done. It's in my fridge.
Okay.
Got a couple bottles.
Well, you should come by then. No, this could be real. There's no reason to just stop here. Do it. It takes me.
So the
an hour to make a pie.
the cider compiler club.
Yeah, exactly. Exactly.
It's weird because I don't drink that much, but I love brewing. So I just end up going to, people invite me over. And I'm like, oh, I'll have a bottle of cider, and they're all.
You can
so
make some
impressed.
friends. Yeah. My problem with most store-bought ciders is they use sulfites to do.
Yeah, I don't.
And the sulfites give me a hangover like nobody's business. But
Don't
a
use any
really
pressure.
plain cider with no sulfites is fine, and not all good.
So I grew up in apple country, so cider was always the droppings. So all the
Right.
apples that drop get turned into cider because everything else has to get shipped off to be sold. So basically,
Right.
if you're drinking cider, like your flora and fauna inside your stomach is pretty amazing because it's on the ground typically for a day before it gets picked up. So you are getting like every piece of bacteria known to man.
Oh yeah. Well, the
If
alcohol.
you can survive
kills all, right?
cider. Well, I'm talking not hard cider. I'm talking
just fresh.
cider.
Oh, maybe.
Well, it ferments a little bit on the ground.
Yeah.
A little bit, maybe.
Right. So I usually, like things like apple butter. This is for the bad. This is for the bad apples, right? But of course, it boils for hours to become cider. 10 hours, 12 hours. There's nothing left in there.
So are you ready for this? So after you make the cider, you take all the dregs, if you will, all the shit that
tailings.
comes out of the press, and you can
Yes.
actually make apple jelly from that. So then, so that's where you really boil and boil and boil. You add some pectin, and then it becomes apple jelly. So it's like nothing goes to waste because then everything left over from that is now recycled for fertilizer. So
Yeah, right. Yeah, what not much can be left from that, but yeah, sure, fine, interesting. I do collect apple syrup from my leftovers for making this stuff because apple syrup I use it in making the pies. But I have now a fair amount of it, more than I want for pies, unless I'm making everybody, a dozen pies or more.
you can make me a dozen pies. I'll take it.
Yeah, they don't ship well. That's the issue. They're easy enough to make, they just don't ship well. You got to come get it.
So have we talked out the preemptive
apple pie thing?
No, I meant the.
I'm sorry, did this make it into the Google Doc so that people can index the apple butter,
totally.
apple cider?
Yeah, it's in there. I didn't do it, but somebody did. It's all good. Oh, I was off by a day and I started this process, and you can't, once you start jarring, you can't stop till it's done. And then my wife calls me, hey, you doing coffee club this morning? No, it's Thursday. Oops. What you gonna do? All right. Yeah, concurrency, continuation passing style. What else is going on here? The whole multi-threading thing. The one other hack I want to mention on that one is I found it very convenient when throwing out continuations by the bajillions to have a common roll-up point that said I forked off a bajillion things, and when they're all done, I want to carry on now with this continuation. And the hack for that was you handed out a gathering place. I call it a futures plural for all your futures independently to be done and come back to, and you could wait on it. And the implementation of the futures plural was this stupid ass trick that would sync literally millions a second of completed futures. So H2O, like farming out billions of units of work. Each unit of work was actually pretty big, and then syncing them at a huge rate. And that one is, you guys had a list of pending known futures that hadn't blocked yet. And when a new one said, hey, when I'm done, I'm going to block here, he would walk the list of pendings up to some depth of, it didn't matter what, And if he found somebody else who had been completed, he would throw them off the list and lower the blocking count. And the end result was that the list typically had 5 to 10 out of millions a second. Like literally it was tiny all the time, because things would just complete so fast, and the next guy in would just strip out a couple things off the list, and you didn't have a giant list of 1 million long. You had to check when it was done or completed, whatever. As things completed, you threw them off. And so you could have billion things launched and millions a second sync rate that was not taking any time at all to sync. And then when the last one was done, you were done immediately off to the next task. So there is a way to support sort of like an enormous rate of task launch, task sync. I guess that my expectation was a task was going to take longer than a time quanta on a processor, so longer than 10 millis typically, but the overheads for launching and syncing a task were actually down where you would be usefully making progress if they were coming in at the high microsecond range. Somewhere around the low microsecond range, you're better off not forking a task.
Yeah, and generally, I think that's what you kind of think of a fiber in that same way. It's something that has to be super, super cheap to create.
Doug Lee fork join thread for me, which is very similar to your fiber, except I did them cross clusters, but that was just a little overhead to get them started on the other guy background.
Give us some time to get the single machine working, right?
Yeah, exactly. Well, that's where I'm at with AA. So I'm not even there. I'm like somewhere down typing theory, and I really should back off from some of this other stuff I'm doing under the hood and just nail the typing game really through the hard theory bit, and then come back around, because I'm already doing a lot of stuff with in the realm of typing that has to do with cleaning up and optimizing the set of things I'm typing, and I don't need to do that. I have to handle a hard problem with the theory anyhow, so I should just do the hard problem.
I'm going to paste in something you might find interesting. I just saw this very recently.
You doing it in the doc here?
Yep, I'll put it as 5. It's it's right up your alley. It's a guy doing another lightweight compiler backend.
See what it says here. Redirect, redirect,
Cwerg.
Ah, there you go. Yep. Dun, 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 dun. Yeah. The issue with JITting that I ran into, and I guess Arthur can talk about this, is not just speed of code generation, but also the tight interaction with the runtime, where you have to bring in profile data and profile data changes, or you have to have ways to have one JITted method call another up until something happens, and then you have to stop having it call it and correct things and run again and stuff. The interaction with the runtime loses a lot. Certainly the Julia code I looked at, which come out LLVM and it was JITted, sucked compared to what I was getting out of like Java or even C code, because the JITting didn't understand how to cross call well. You would think so. There should be some way to set up LLVM. Maybe the Julia folks just weren't there, but definitely every cross call from Julia JITted to Julia JITted code went through extra trampoline layers and the expensive kind of call. So
Arthur must be able to tell you by now.
He's still here? Oh, he's there.
Oh, what was it about the call through a register indirection instead of calling into immediate?
Yeah,
yes. I think
there's definitely a call through a register, and I want to say it trampolined once as well.
Well, the call through immediate instead of a register, I think we fixed that upstream. I'll need to double check. We had this issue with calling to some stubs, and yeah, that hurt performance in some cases, and that was in the workings. I don't know if it landed or not.
Okay.
And about the trampoline.
Yeah, the Julia code I was looking at was definitely dead. And besides being expensive as a x86, it also drowns your branch target buffer, which means your actual virtual calls don't get a branch target buffer anymore because they're beating.
Yeah, but you need to know that your target is within 32-bit address.
Yeah, well, and right, but that one's
So
again. Oh, maybe this is LLVM. Again, this is like JITting code. It's all going to be within 4 gigs. You just lay outside of 4 gig space and say all the code lands here, and therefore it's all within 32-bit, offset range.
Yeah, well, you'll need to communicate this fact somehow to LLVM so as to get the proper loading.
Right. One of many issues with LLVM as a JIT, which maybe it should be solvable. Shouldn't be too hard in theory. Just been at it a long time. I haven't seen it happen yet, but maybe you're going to do it too, or you've done it already. It'd be good. That's
Actually, on the topics of JITs, there's a couple of sort of questions I have, because I've been looking into that a bit lately, kind of as part of my whole sort of compiler re-engineering for my language. Like I'm rewriting my compiler in Rust. I'm now sort of looking, okay, what intermediate representations am I going to use? How many? Sort of how would that affect a future JIT? I'm kind of curious that this isn't always clear to me, like when you have a function that can be JITted at runtime, like how would you make sure that when the function is JITted, you use the JITted version, and if not the interpreted version? Because the simple case that I can think of is you do your method lookup, you get some sort of structure, and you say, oh hey, if the JITted code field is set, then call that as an actual function, else do this other thing. But then you have this branching overhead.
Right.
It's going to fail for a bit and then it's going to pass. But if you de-optimize, then it's going to fail again.
Yeah. Right. Okay. So
how would you handle that?
Right. So this is a handoffs. So the hotspot version of this was everyone had an entry point that was the favorite entry point. And then if you came from the interpreter, you had to call the interpreter favorite entry point. And if you came from JITted code, you went to the JITted code favorite entry point. And then the JITted code favorite entry point, if your target method had, the goal here was JITted calling JITted had no overhead, literally none, same as static compilation. So JITted calling JITted was, I had an x86 call instruction with an offset that mentioned directly the JITted entry point of the target. So that's your end goal. Now you're going to work backwards from there. So if JITted calls interpreted, there's a JITted entry point that shuffles the arguments such that you can now call the interpreter and it bottoms out with a jump to the interpreter. And vice versa, if the interpreter makes a call, he can do a slow thing because he's already slow, but he's going to do a lookup and get a favorite entry point from the interpreter, which if the target is also the interpreter, turns out to have very little overhead and you just go to the interpreter again. But if the target is JITted, it's the reverse shuffle of your arguments. And then you call into the JITted guy, or trampolines, it jumps, and then calls, it jumps into the JITted code. So there's trampolines that were based on signature, and the signature generator inside a hotspot takes a source signature and a desk signature, and the source signature is a standard method called signature plus I'm coming from interpreted or compiled from JITted or native C code to a target, which was interpreted, JITted, or native C code. And it just did the arg shuffle and then it cached them. And any given large Java program, you'd cache a few thousand of these and never again. So the actual generator was 1,000 lines of C code that walked the signature and just put down register shuffle bits into a buffer and declared a code buffer. And then, you did a caching lookup on the signature. You got a hit in the cache, you pulled the old one out, whatever, fine. So the actual cost to do the trampoline was, it depends on your size of your signature, a dozen clock cycles. You didn't care because you were coming from or going to the interpreter where you sucked. So dozen clock cycles, no big deal. Once you're in the JITted to JITted sequence, life is good and you're running as fast as you can ever get. And then there's a Deopt, and the Deopt has a separate set of issues you have to all handle all at the same time. Running processors will continue to run on code even as you try to tell them to stop. If you try to edit the method call buffers, people have them cached in their iCaches and shit like that. So you have to deal with a bunch of cases before you stop having people make the call into the JITted method. So for whatever reason, the target method has now been declared bad. And the issue is it has threads running in it. It has threads who've called into it and called down below and will return back to it. It has people who are in the middle of making a trampoline call into it. Okay, and these are all things that you can't actually stop. So the first thing you do is you go into the vtable that you did your lookup on and we're jumping to, and you change the targeted method, the desired method entry to be the interpreter who always does things the slow right way. And then that doesn't catch everyone who's running through a trampoline. And then you put down, and so the reason this guy's failing out is because it can be as bad as you want to load another class that made this code invalid. You can't let that class load yet because this guy's still making calls on the old code, which knows in its heart of hearts that it's loading the single only valid class implementation there is and inline the hell out of it. So he cannot, you cannot load the new class and make a new instance and publish it and immediately you're incorrect. So the class loading stalls. So till you fix this problem. Now you have guys in the trampoline, you go to the head of this method that says, I don't want you to run anymore, and you stomp it with a jump to go to the interpreter cleanup point. And you've already fixed the other way so that when you jump to the interpreter's, the JITted to interpreter entry point, he will actually end up in the interpreter. And we've had bugs, of course, where you waffle back and forth 1,000 times between calling the JITted to the interpreter to the JITted to the interpreter without actually making any progress until you got the cycle closed. But you do the right order. You have to do some atomic forcing, fencing to make sure that things are happening there. The guys are going to.
So you just interrupt because this is like a whirlwind of information.
Yeah, okay, slow down.
Like already happened.
Yeah, right.
But so the basic premise, if I understand it correctly, is you have whatever structure you have to represent your method with whatever metadata your runtime needs. Then you have some sort of field in there that lists the instructions the interpreter would run, I would imagine.
You have a field that is the entry point that you would take coming from JITted to go to the interpreter. And the entry
right, but so that's where it's a little confused because I can see if you have, let's say you call. So one way I would imagine you could do this is you take your list of instructions from the interpreter, you start running them, and then the very first one is that basically says, oh, hey, we are JITted, jump here instead, or call this function, something like that.
Right, you come to a method call in the interpreter.
Yeah, so basically you do your lookup, at that point the interpreter is still like, oh, this might be interpreted, so it takes the instructions, it prepares the call stack, whatever it does, and then it runs the first instruction, which that would, and that one is basically, hey, call this function instead, or does it decide that before then?
Yeah, So the mistake to not make is to push on a frame that is not a frame that you want to end up being in.
Right.
So never add a frame until you got the right target.
Right.
Okay. So from the interpreter, you're going to load up. For me, I loaded a field which was I'm coming from the interpreter calling this other method. So I went to that method. I said, give me your interpreted entry point. Now, if he had a JITted method also, that interpreted entry point did the shuffle and jumped to the JITted code.
Right.
So I always said, give me the interpreter entry point and I'm going to call it.
Right. And then so, but that's, I guess.
That's a standard x86 call register. Load up.
No, I think I might have explained wrong. So maybe I can show it. That might be a little easier to explain.
Yeah, this is right on stack replacement.
Hold on, let me hide some stuff.
On stack replacement jargon, because the hotspot OSR and Deopt are backwards from a lot of other people in the industry, even though hotspot did it first.
Right. Let me share my screen to just show because it's probably a little easier. Oh, I can't share it. I need permissions for that.
Didn't I throw doc permissions? The other people are editing.
Done in 1994.
No, screen share. Sorry.
Oh, you want screen share? I'm sorry.
Yeah, so I can just show it. That might be a little easier to sort of explain.
Try it now.
Let me make sure it's the right window. Yeah, there we go. So is the font size large enough, or shall I crank it up a little?
I got it.
Let me crank it up a little.
My monitor is wider than yours by another foot. But I do 3 windows across too.
Yeah, let me get those out of the way. So that's what I have here, like my structure for methods. You know, it has my header, which has the class in it, the name, file, all the stuff.
Yeah.
Then here I have a field which lists the interpreter instructions to run.
Yes.
So and each instruction is
another field, which is your JITed code, binary buffer, right. Actual x86 code.
Right. And so then the interpreter, it will basically do its method lookup, and then I guess it would say, hey, if we're coming from the interpreter, just get the interpreter instructions, run those.
Okay.
Or does it already decide there, hey, if the...
Yeah, so the calling guy goes to the called method. So I think I'm looking at struct method here on line 28. That is the called target method I'm trying to get to.
Yeah.
So I go to that method, and he has a field that says, this is the interpreter entry point.
Yeah.
So he loads that field. That's already a pointer to machine code, and he jumps to it. Or he calls to it. Classic x86 call.
Wait, so then...
For that to work, you need a few other things set up.
Right, but so does that mean that in... let me stop this.
Yeah.
Because it's one of the difficulties that's like not really easy to find info on.
Yeah.
So what you're saying is basically, you know, when you load a method, it already has like a bit of basically dynamically generated code that decides, hey, we need to interpret or JIT call this thing, or...
Right. Yes. Let me back up.
Right.
In Go, JITed to JITed is as fast as it possibly can. So the JITed call has no fucking clue if his target is interpreted or JITed. So he will call an interpreted method the same as he calls a JITed method. So that interpreted method needs to have a piece of machine code that can take a call from another piece of JITed code and take off and run in the interpreter. So right away, an interpreted method needs to have a machine code entry point that is suitable for calling from JITed code. As soon as you have one machine code entry point, it's easy enough to have a second. It's hard to get one. Now you get one, you can have a second one. The second one's interpreted.
All right. So basically, when the runtime defines the method, it sort of immediately generates what is essentially a stop function, I guess, which by default, I guess, jumps to the interpreted code.
Yeah, right. So if I have an interpreted entry point and a JITed entry point. If I have no JITed code, no one calls the JITed entry point, so I can just put it off to a crash me down. But if I have an interpreted entry point that I'm calling from the interpreted, then I can assume that that set of arguments are all perfectly aligned. The interpreter calls itself just normally, and that entry point can literally just be the address of the interpreter itself.
All right, yeah, because so my thought process basically, when you do the lookup, you effectively have an if that says, oh, if this thing is JITed, you know, call this function else.
Right. The JITed code doesn't want to do that if. So the JITed code is going to jump to an address, period, end of statement, bam. Okay, now that it's only jumping to an address, the interpreter can jump to a similar address.
Right, and I guess so you either have, I guess, two entry points or one that you update if needed, I guess.
There are two, one coming from the interpreter, one coming from JITed code. And then what they do depends on whether the target is JITed or the target is interpreted.
So you're writing this down?
Yeah, no, it's all good. This is stuff I don't get to talk about very often, and it's key to how the Java runs a billion machines the world over, and it's not well known. It's like, shit, folks.
No, because Like the backstory is, right now I don't have a JIT. It's probably going to be a couple of years before I have a JIT. The reason I sort of started looking into this because I'm redesigning my compiler, and as part of that, I was like, okay, just to sort of think about it, not necessarily implement. What would I want to do, or what should I do if I want to make my FFI faster? Because now I use libFFI and it works, but it's a bit clunky. And in my case, my runtime is written in Rust, and I have to ship libFFI. And
you can go right. You can do the FFI thing before you get a JIT and have the FFI.
Yeah. So my thought process there is essentially as sort of a starting point for a JIT, you could write a JIT that just JITs your FFI calls.
It was easier to not go officially to a JIT there. Really, it was too simple. And it's all about register shuffling, which goes to register allocation in the JIT, which is always one of the harder parts of the JIT. So
it's not like an actual JIT because you're not swapping out methods.
This is your step into machine code.
Yeah.
Not necessarily yet the JIT.
The challenge there, though, is I think if you have, say, you have your interpreted code, you have a bunch of interpreted function calls, and then you get a JITed FFI call.
Yeah.
You probably need an extra instruction that says, hey, we're doing a native call, basically. Look up your function here.
Yeah. So the interpreter will do a grab the method, and he wants to grab the interpreted method entry point. If the method he grabs is an FFI, then his interpreter entry point is the argument shuffle to the FFI code.
Right. No, but so that's kind of where I start thinking, like, okay, but then if you take that further to like a proper JIT, like how the hell are you gonna make it so you can sort of swap a method with its JITed version? Preferably without messing with too many atomics and locks and whatever, and without having to do this branching every single fucking time.
Right. So you have to think about it, not the branching every time. That's the thing you want. That's what I'm whining about with Julia. They're doing the branching every time, and
no,
several other Java JITs have this problem.
Yeah, and then there were things like this. One of several reasons why probably JIT is still pretty far off. It's because all the code in your interpreter that it's least used for handling instructions, to a certain degree, you have to duplicate that. For like integer addition, that's pretty simple, not a big deal. But I have an instruction which is basically write a value to a future and then handle cases where, if the future is already closed, do this other thing. And
you don't have to do all of that in the JIT though. You can transfer control to the interpreter at any point and transfer back.
So the idea I had, what you could do there is shove that logic in a function. This was my thought process, right? It's a function that you forcefully inline in the interpreter, but still allow the JIT to call directly, which means you do have the function overhead, but you don't have to duplicate, I don't know how many lines of code.
No. Okay. So always the JIT is does the normal 3 address RISC thing with a C-like kind of execution model. Then you get to cheat and take shortcuts and call back to the interpreter where you don't want to deal.
Right.
So you can incrementally deal with things that are complicated. Now, do your future game. I do that kind of stuff in the hotspot JIT, not the future game directly, but there's a bunch of things where I have complicated control flow that all I did was I wrote a little piece of a convenient way to a toolkit build up IR that was kind of complicated. There are IR toolkits in C2 that lets me, in short, easy syntax kind of things, write up big chunks of IR that do a complicated job. If it got more complicated than that, then I also had Java code I snuck off to the side, Java bytecode, I snuck off to the side, that I would just feed in as a method call that was happened to be targeted or tuned such that it was guaranteed hot inlined every time.
Right. Yeah, because that's
what they call the intrinsics now, I think.
Yeah. The intrinsics were all hot inline Java code. Well, some of them were, and some of them are handcrafted machine code, handcrafted IR.
So I am kind of curious. Let's say you have simplified. Let's say you have 3 instructions in your instruction set, and 2 are the kind of instruction where JIT will benefit, like some numeric stuff. And then the third one is something like, I don't know, send a photo to my printer. Like, I don't know, something stupid, where all the overhead is not in the interpreter.
Right.
I think for that, you'd probably need a tracing JIT. If you have a method JIT, how you basically generate your code for those two instructions. And then the third one's like, how would you jump back in the interpreter?
Okay.
You call it. No, you just call the same function from your interpreter that you call from the JIT code.
Right, but so that's the thing, that in the interpreter, all that code is, or at least a big portion of that is inlined. So if I have, my 3 instructions, for the numerical ones, it's probably just one line of code that you write in your interpreter. For the send a photo to my printer thing, it might call a bunch of functions. Some of those might be inlined, some of them are not. And one idea I had, you could move all of that into a function, forcefully inline in the interpreter and call that from the JIT. But then you have that function call overhead.
You're missing the key bits here and the difference between tracing and not tracing. So this is unrelated to tracing JITs.
Right.
A method entry JIT, in my opinion, does better than a tracing JIT because it gets more stayed around. But that's an argument about tracing method JITs. So
I would argue that.
Let's not go there. Okay, I'll agree that it's a contention point. Let's cover this other piece first. So you can always stop the parsing bytecodes in the JIT and bail out to the interpreter. So that's de-optimization. And the goal there is to not deal with things that you don't want to deal with. And you can incrementally add the dealing with later as you get more and more and more performance. But the first cut is, I don't like to deal with this in the JIT. I'm not going to. I'm just going to jump to the interpreter at this bytecode offset and go. So there's that handling of things I don't like. And then the other one is, you're a complicated guy, you turn into a method call to an FFI, and then the JIT guy makes a method call to the FFI too. Right? It's all, you can all hide all your send a photo to the printer hides in some other thing. And you just call it JIT code wants to call FFI, same as he's calling other methods.
That's what I meant. That's what I meant.
Yeah, there's always a bailout here. The two bailouts, I call it, I deopt to the interpreter.
Right. Yeah. I think the challenge here, I'm trying to sort of visualize how, like if you write a JIT, you essentially, you have your interpreter on one end, and then your JIT compiler has sort of these similar kind of loop where it goes through the instructions, but instead of running them, it emits machine code. I'm just trying to look like, okay, you have your 2 numerical ones, it emits machine code. Then for your complicated one, it needs to emit something that is basically go back to the interpreter, and then after that, go back to the JIT code.
But you're heading the right path. So when I parse Java bytecodes, I emit IR for every bytecode, as just like you were saying, all the way down the line until I come to bytecodes that I don't necessarily like. So for instance, I do a check cast bytecode, and I don't like the throw. The throw is hard. So I throw in IR to do the test that says if instance of that IR all goes in. If it's the nut and you're going to fail and you're going to throw a check cast exception, class cast, whatever, I deopt. So I don't deal. So I make a path, a free bailout from the JIT code where I don't like it. It's the de-optimization path. And that turns out to be, that's all the handle you need. It covers all kinds of sins where you don't care. There are other sins you don't care, like this code's never executed before. Why the hell are you spending time JITting code on it? It's never executed yet, right? So there's all kinds of, like, I've never had a null here. I've never had a this, that, fail, that. Well, there's a bunch of these things where you just stop now, go to the interpreter, should it ever arise. And then, if it arises, you have to deal. If it's hot, you'll come back in and improve the JIT, make it handle that case. Or if it's hot, you'll re-JIT with better profiling data and do something different. But don't deal.
Right. So I'm guessing in that case, what you probably do is you'd generate the machine code for the 2 instructions you're interested in. Then when you hit the one you're not interested in, I guess you would generate some code that says, hey, we are at instruction offset X. Prepare my whatever frames I might need for the interpreter. And instead of the index starting at effectively 0, start at this offset.
Yep.
Right. Okay.
Yeah. And I would argue.
Sorry, go ahead.
Before we dive into this mechanics, I would argue that a method JIT with inlining and ability to de-optimize is essentially a tracing JIT, because you can stop at any point byte deoptimization and switching to interpreter, and you can inline into like anything you want. So basically, you can choose any trace you want to optimize. Yeah, and with OSR,
you need to entry at any point too. Yeah.
That's the way in the other direction.
Yeah.
So that's why dichotomy between tracing and method. Well, I think they are pretty equivalent if you add the ability to switch back and forth between compile code and interpret code.
Right. Yeah. My sort of difference there is basically in my head, a method JIT is something where the entire method is JITed. It's just JITed code, whereas tracing is more like some sections of it might be.
I've stared at the history of tracing and method jets for a long time, because obviously that was the competitor to Hotspot's method jet. And obviously people went back and forth, and tracing jets have their easy get going and startup things, and different issues arose. And all the guys doing tracing jets never caught up to Hotspot's method jet. Now, you could argue that that's inherent to tracing jets, and you could argue that I did a great job. And you could argue that it was just, I started ahead of them and they just needed more time and they were going to get there, and maybe they got there now. So,
yeah, because like the the backstory is like my VM has fairly high level instructions. A lot of them I have moved into
high level instruction, yeah.
No, but like fairly high level ones, like send a message to a different process, which involves putting some data in the queue, checking some stuff. Do we need to reschedule the process, etc.?
I imagine Cameron's ecstasy should have something. Would have something.
It's similar in that regard.
So,
and
no, our IL is so abstract that the same call is used to call an inline function as it is to send something across a service boundary.
Okay, fine.
Right. Yes. So in my case, I mean, I have instruction like normal method calls and such, and then essentially sending a message to a process. It's kind of like a method call, like it still does the normal method call lookup, etc. But then what it essentially does, it takes the pointer to that method and just puts it in the queue of the receiver along with the pointers to the arguments. And then at some point, the receiver takes that and it creates its stack frame and everything, and off it goes.
I heard a red flag I want to make clear, but maybe I didn't hear it right, which is separate out implementation semantics. That there's a semantics that says I pushed a message into another guy's queue, and he could take it when he wants to. And there's an implementation which the interpreter does. And you can imagine you want the JIT to have the power to say, I'm going to inline this entire other process right here, right now. I'm going to not put the message in the queue. I'm just going to execute as if it were in the queue already. And I want to have it well specified what it means. And I want to not be forced to jam it into a message queue because somebody else knows in its heart of hearts that it got in some queue and you can look at it. And I can't, as if my way away from doing the message send to just inlining the sucker.
Right.
I want to make sure you have all the way down.
So that's what I'm not doing. Basically, if you have a process, it's guaranteed to be a separate thing. There's no inlining across process boundaries. Maybe 20 years from now, I might do that. Sorry?
I heard you say you're guaranteed there's no inlining across process boundaries.
Yes.
And I would claim that inlining should always be an as if you can't tell, you can't tell. So make it so that you can't tell, and then the JIT does what the JIT wants to. It makes it go fast.
Yeah, but it's mostly because for inlining across process boundaries, I think given what you would use it for, it's not that useful.
And small and called a lot, it's useful.
Yeah, the benefit of the messaging is the rest of the system sort of built around this idea that they are isolated.
Yeah.
Yeah.
I have a random number generator as a service, as a process. I want to call and get back random numbers. I'm running a Monte Carlo simulation. I want 1 billion a second. There's an obvious semantic to the random number generator that you can't tell as if I've inlined it. Why not fucking inline it?
No, so in the language, it's not visible, but at least for the foreseeable future, if you send a message to a process, it won't inline the code that handles that
This
message.
is your decision at the moment, but
probably a decision forever.
Okay. Well, fair enough. I mean, I'm trying to talk you into not boxing yourself in where you can't
Right.
unwind that decision. If you
No,
just-
so the key difference there, though, it is, should I ever make a language spec? It's not part of that spec. The spec won't say, we guarantee this will never be inline. It's more like, in practice, we won't, unless at some point we decide, somebody convinced me otherwise.
Yeah, fine.
Well, my point is more like the code for those instructions is fairly complex in the sense that you can't just quickly generate some equivalent JIT code. No, instead you have to copy the code you call directly, probably everything that's inlined, and you end up.
Well, right. I have a wad of machine code I'm just going to template slap in, and then there's I just have some Inco code, C code, Java code that is kind of complicated, and let the JIT go to town with it. The JIT does what the JIT does. And then this code calls other code and does this. The JIT does what the JIT does, and the JIT happily inlines all the way down and does a hot path profiling job on you and takes all your weird corner cases and deopts the interpreter, and otherwise it gives you, straight line code that does all the complicated shit fast. I mean, if you steer away from having templates that you slap down, you can go a long ways with performance.
Yeah, I probably wasn't gonna do the template JIT approach. I did think of it.
Not template JIT, I meant template for complicated things that show up in your hot.
Oh, right.
Right. Like if I do a garbage, a new allocation. So over the years, the code for new allocation kept changing, but always there is this theory that the garbage collector, the JIT doesn't want to deal with the garbage collection. So if you ran out of memory, you blocked and you ran off, and the GC did what it does. But the allocator, waffled around left and right the actual allocation. But usually it was take a pointer, bump it, grab another pointer, diff the two, inbounds, done. It's like super fast. Arrange yourself that you can write yourself as a bunch of IR, and then for these common operations with a bailout when shit gets ugly.
Right, and there's some approaches, like there was a project a couple of years ago from Mozilla, which they called a holy JIT, where you would write your interpreter loop in Rust, and then I think they hacked the Rust compiler so that with some annotations it would generate a JIT from it.
I've seen people do that. Yeah,
There's
limits to how far you go there. But
the performance, from what I understood, wasn't as good as a handwritten JIT, but it also required only 10% of the effort.
Yeah, I've heard about these things. I've seen them actually in action a couple times.
It's like unfortunately that particular project is like most of them, people stopped working on it. And I've been looking at some alternative libraries. There exist some in Rust, but I think in all cases the concern is I'm not sure if they will still exist 5 years from now. And I think a JIT is one of those things that's often quite integral to your runtime.
Yes.
And if you use a third-party library, you might end up with cases where they decide to do things differently.
We didn't talk about what happens, how you unwind in these cases when the JIT's done an aggressive optimization that has to be unwound, and that's
and so
runtime now.
Like in this case, for example, there's a Rust library for JITting called crane lift, and it's used by some WebAssembly runtimes.
Okay.
But they have their own IR and some own stuff, and I was kind of thinking like in a way, it feels a bit weird that you have your bytecode, which is effectively already in IR. You then stuff that through JIT IR, and then you get your machine code. Whereas in theory, if you have a bytecode compiler that produces good bytecode, that JIT IR wouldn't really be needed. You could, in theory, go from your bytecode straight to machine code, but this is me saying never having written a JIT.
Yeah, so this is a topic they call MLIR, so mid-level IR. So so like a Java bytecode, for example, is what we call a high-level IR.
Yeah.
Although it has plenty of low-level crap in it, but it's a high-level IR.
The high-level IR, yeah.
And then x86 is your low-level.
Right. And now you have a mid-level.
x86 assembly is your low-level. So
Yeah.
x86 machine code is the output.
Yeah.
And so if you don't want to be working directly in the high-level one, and you don't want to be working directly in the low-level one, what you do is you create this mid-level IR which basically bridges the two domains. So you have things in the high level IR domain that really do not belong in, do not directly intersect with the low level. In other words, I have one, like you were asking earlier, York, you have one instruction that produces 1,200,000 low-level instructions, right? And that's perfectly valid, but the thing that produces them is the thing in the middle. That's the mid-level IR.
Yeah.
It breaks down some of those big concepts. They're still not low level, but they're, you know, so it's the bridge, I guess.
Sea of nodes
I would-
at level IR.
I would argue that the problem with Java bytecode is not that that's not that it's an appropriate level of abstraction. We can't do useful thing at this level of abstraction. It's just very inconvenient to analyze and modify. If you ever try to write any modification on Java bytecode, like, yeah, no fun. And in general,
you have to reload it into some other IR and repack it entirely and put it back. It's just like, no.
So I did when I built a incremental Java compiler. Yeah.
You know, my first job at Sun before I did C2, and you guys probably didn't know I had a job at Sun before I did C2, was to go do some low-level Java bytecode optimization hacks. And I couldn't do anything except like load it up into a real IR, modify it, and then put it back down into bytecodes with basically register allocation and code generation, and a bunch of the parts could not be skipped because it's a pain in the butt to mutate that shit. Yeah.
And the biggest problem, by the way, is that any change you make inside a method's Java bytecode, you then have to rewrite the entire constant pool.
Oh yeah.
And to rewrite the constant pool, you have to disassemble the existing methods, every single method in the class, you have to disassemble to the old constant pool and then reassemble with the new constant pool. So that's why in Ecstasy and IR, that's one of the reasons why I produce what's called a local constant table, which is not actually a constant pool. It's just a indirection. It's an indirection table. So it's so that way you don't have to disassemble any of the other methods. You only have to rewrite their indirection tables. And so every opcode only references the local table. So that also helps with opcode compression. So just lessons learned from rewriting Java bytecodes.
If you're looking for a different high-level IR than Java bytecodes, around the time that bytecodes were coming out, there were a lot of people doing interesting work on, isn't there a better set of bytecode-like things we could do? And there were a lot of good papers that came out of that had all kinds of higher compression, easier to modify, easier to JIT and for a template JIT and all kinds of stuff. But you know, the horse left the barn, and here we are. We got x86 to write our machine code to. We got Java bytecodes to write it from. Both ends suck. All right, well, we're noon. I got stopped on a rant on our role on what to do with, you know, Deopt and how to handle your runtime with code gen on the fly. So there's, you know, grist for the mill next time. I guess I'll take any last questions here before we call it a deal.
I think York would be fine if you just show them by taking Inco and writing a back end for it.
There you go.
With a de-optimizing.
Well, if he writes an AA front end, I'll write the Inco back end.
Oh, I spent the last 6 months changing my whole type system in runtime, and I probably still have a few months to go to finish my compiler. Maybe in a year or two.
There you go.
Like JIT is still way off. It's more like I'm just slowly starting to take a look at it and trying to figure out if there's any sort of big decisions I need to make now that perhaps make my life easier 2 years down the road.
There are some things you can do in DIR to make dynamic de-optimization easier. I've added links in Google Docs. The last one is in particular correctness of speculative optimizations of dynamic de-optimization. They have some examples of how you can make your job easier in the IR.
There are a lot of very interesting, difficult to diagnose bugs that came around with the dynamic optimizations in Java that, you know, eventually got sorted out. You know, those all got beaten out years ago, but it took years to get them found and beaten out. All kinds of fun things you can do, and then trouble you can get yourself into. All right. There's a lot of reading there. So I got my reading set out for me here. Until we meet again. Yeah, so next week. Feel free to poke me if I haven't sent an email out because I'm busy jarring the next round of apples. All right, bye-bye.
Thanks for hosting.